Hi, my name is Anran.
Hi, my name is Yicheng. We are advised by Professor Tseng from Boston College. We are glad to present this poster, CarML, Distributed Machine Learning in Vehicular Clouds. Nowadays, machine learning is widely used in many industries to analyze data and help the decision-making process. However, large data sets require lots of computation power to process. A centralized design can be too expensive, so distributed machine learning has been proposed to address this issue. Basically, distributed machine learning splits up the work and sends small data batches to workers to perform training. It will reduce the need for high computational power on one single machine. The distributed machine learning model we focus on is parameter server.
So why do we propose the CarML architecture? In CarML, vehicles are used as a new computation resource. Nowadays, many smart vehicles have enough computation power and communication capability to perform training tasks. For example, modern Tesla models are equipped with chips specialized for machine learning and dual computers for backup. So when the onboard computers remain idle, we can utilize this computation power, given the size of the vehicles on the road, to generate tremendous computing power to train on large data set. To give a general walkthrough of our poster, first, we propose CarML, an architecture for distributed machine learning in vehicular clouds. Alongside, we presented our simulator built using Python and Sumo, which considers many factors, such as vehicle mobility, communication methods, and failure cases. Last but not least, we showcase our algorithm for improving fault tolerance and performance in the results we obtain from comparing them to traditional solutions. This slide here shows the three-layer architecture and communication methods of Cardinal. The top layer is the cloud server, the middle layer is made of roadside units, and the bottom layer consists of vehicles. Based on current technology, we have envisioned the communication methods between each layer will be shown as in the figure, where cloud server and RSUs communicate via local area networks, RSUs and vehicles via millimeter wave, and the vehicle and cloud server via 4G or 5G cellular networks. Continue from the previous slide, we'll show how data flows in between the architecture. In the beginning, the data set and the model are stored inside the cloud server, and partitions of the training data are distributed to each RSU from the cloud server. Each RSU assigns mini batches of training data to vehicles within its range. Then vehicles upload the output gradients back to the RSUs after training. The RSUs will then upload the average of the gradients to the cloud server to obtain an updated model for the next iteration. Each vehicle can also choose to communicate with the cloud server and update the model directly.
In our research, we also studied technical challenges that would occur in reality. Due to the limited time we have, we will demo one experiment about RSU placement. So, why do we want to study RSU placement? Imagine the case shown in the plot where we only have a limited number of RSU in a city. Each RSU covers a fixed range indicated by the purple circles. Only in the range, vehicles and RSU can communicate with each other. Therefore, if RSU are placed at locations that have many vehicles passing by, more data in RSU can be distributed to vehicles. Knowing the importance of placement, we ran the experiment. We compared a random approach and an optimal approach with their resulting maps shown on the slide. The map is based on a part of London. Using the dbScan algorithm, we clustered the roads into segments based on traffic and represented traffic density with different colors. Black indicates high traffic density, while blue indicates relatively low traffic density. The red stars indicates the RSU locations. As you can see on the plot on the left, the random approach puts RSU randomly, regardless of traffic density. In contrast, as the plot on the right shows, the dbScan approach puts RSU at the locations with the highest traffic density. Now, on this slide, we show the performance comparison. Overall, as it is shown on the plot, the dbScan approach outperforms the random approach by 50 to 100%.
And to summarize, we have introduced a new distributed machine learning platform, CarML, that's built upon vehicular clouds. We've also showcased our simulator and algorithm for higher performance and fault tolerance. Our future work will focus on extending onto more ML paradigms, such as failure learning, as well as working on building a more scalable and realistic simulator.
Thank you for watching.
Thank you.